It's not a quiz. You can talk. You don't have to whisper. Always. If I put you to work, you can talk. You can get help.
I first draw delta x. So that's delta x in a small change. And I draw the bar chart. And then we're going to rotate it around. So I just trying to picture that bar. And I wrap it.
Okay, so you're not spinning your wheels on that function. Here is y equals 3 over x squared. Okay? Okay, so take a look at, this is x varying through delta x intervals. Did you get this far? Hopefully you made it this far. Anyone able to get this? So, yeah, some people got it. Good. Good. That's the easier one. Y is harder. Y is harder. Any questions about that? So the hardest thing about this is the radius, right? The radius of your cylinder is a large variation in x, right? It's not an x coordinate because it starts, x starts varying at 1 and comes in like here. And then our final, so the radius is actually, this left side is our x value, and it's coming in this way. And our center of rotation is 4. So that's a large variation in x, and so it's going to be x final, or x2, minus x initial, or 4 minus x. Because this over here is the x value in the cylinders. So now these cylinders, when you make these cylinders, each cylinder is inside all the other ones. Every time we've seen this before, the cylinders were wrapping around each other as the variable increases. Now these cylinders are kind of, each one is enclosed in all the others as x increases. Do you see that? They're getting skinnier, they're getting smaller and smaller radius as x increases. So the last one is this one of least radius down here. So each one is inside all the previous ones as x increases. Can you imagine that? Can you imagine? That's important. All right, questions on x setup? Okay, so let's if you're started on y, that's good. Let's give it a shot here. It's harder. See if I can erase only the orange. So now y is increasing through delta y intervals. Still got the same empty. Here's the empty shell. It's this. Don't know how to describe that, but that's what it is. It's got a hole in the bottom. So it's kind of like another kind of bowl here with a big hole in the bottom of it. Okay. So now with delta y intervals, we're gonna. What do we do? We're going to pick a delta y interval here, say right there. And we'll do blue. And so we're going to make a strip in that current delta y interval, but not the whole delta y interval. Something like that. So that this distance here, what's that thickness right there? So y is increasing through delta y intervals. What does that mean? That means that this whole thing right here is delta y, as a delta y interval. And then the cylinder is formed This is y. The top of that thing is y, and that's increasing through the interval. So y starts there, and y increases up to there, and this cylinder will grow in thickness this way as we go. All right, and so then we take that strip, we revolve it the same way we revolve to get the shell, and what are we going to have? We're going to have one of these. When I revolve that strip, that little dy strip, right? So that dimension is dy. dy is increasing in the delta y interval. So what is increasing in the delta y interval? What's increasing about this ring? Its radius or its height? Yeah, the height is at the y value, right? The top of the ring is at the y value, and y is increasing. So y is increasing, that's at the top of that ring. So the height's increasing, therefore rate of change is? Area of the base, right? If the height is increasing in your cylinders, it's the area of the base, or this face, right? This face where the volume is growing, the magnitude of that face is going to be the rate of change. So that's going to be pi r outer squared minus pi r inner squared. Okay, and so now we got to get these radii in terms of what variable? Y, right? So we need the y variables. Okay, so outside radius. Outside radius, start with that. What's the outside radius of these? Oops. That's it right there. That's the outside radius. Radius outer. What is that? 3. Always 3 for all of them, right? Because this is constant right here. Center of rotation is at 4. This is at x equals 1. So the outer radius is always 3. Phew, that helps, right? Do you see it? Okay, what's the inner radius? What's the inner radius? Well, is it x coordinate, y coordinate, big variation in x, big variation in y? Big variation in x. So it's going to be x final minus x initial. It's the same thing that we had before for the radius of this one, right? Isn't it 4 minus x again? Do you see it? X final minus x initial, which is just the x coordinate of that curve. All right, and then we got to get that in terms of y, because we're doing y, our independent variable is y. So what is x in terms of y? So pi times 4 minus, we need to get this, so let's see, it's going to be x squared equals 3 over y. Yeah, square root of 3 over y. And solving for x. Solve this for x, and you get? And that 4 minus that whole thing squared. So there's the rate of change function. That's R2 for y, R2 of y. The second rate function, if you use y as the independent variable. Ask me. Ask me. So now there's another complication to this. Does anyone see the other complication to using y intervals?
Or you can have 2 integrals.
Okay, y 2 integrals. He's saying there's going to be 2 integrals. We actually have to split this up when we do it in terms of y. Do you see y? With y, you have to split it up. Why? Because there's this little part down here from x, y equals 0 up to here. I'll divide it out. That's different, right? I should have drawn this. This should be higher up like this. All right, so we're not going to do it. We got that was good practice, and we got to move on. But when y goes from 0 to, I think this is 1/3. Yep. When y goes from 0 to 1/3, you're going to have a different rate function because it's not based on this curve. The inner radius, it's actually easier. The inner radius is 1, and the outer radius is 4. And then once you get to this y equals 1/3, from 1/3 up to 3, from 1/3 up to 3, you have this rate function. So you're going to have the integral from 0 to, well, so we'd have to build a piecewise, right? We have to build a piecewise rate function. But just want to point that out. But we got the practice from building these rate functions, and I want to move on. So this be, if you have time in recitation, this would be a good one to finish. Get the actual volume accumulation function, or good for your studying for review. Find the actual volume accumulation in terms of y. You're going to have to build a piecewise accumulation function. You're going to have a rate function down here, and then starting at y equals 1/3, you have another rate function going up that way. And then what statement would we have? So we're going to have V1 and V2. What statement would we have that shows two ways to get the whole volume of the whole filled solid? So we're going to have V1 and V2. So it'd be V1 of what? V1 of x is going to vary from 1 to 3. So it'd be V1 of 3 would get the whole volume. And V2 of also 3, coincidentally. Not always going to be the case, but in this case, going from 0 up to 3 gets you the whole volume. Okay, so finish this example on your own. Finish that second volume accumulation function for y. But any questions on what we did? Getting those two rate functions. Ask if you're not sure about something. Okay, here we go. So let's talk about, just briefly talk about, can I erase? You have a question? Okay. Can I erase what's on the board? Can I erase what's up there? Can I take off what's up there? Okay. We can come back to it after class if you want to look at it after class. Sure. Okay, here we go. So let's talk about arc length. So suppose you have a football stadium and you're interested in how much siding will be required for the perimeter. So we could model that arena with a graph. And what we want to do is we want to calculate the graph's arc length. And that would help us to determine, say, like how much siding you would need or how much fence or something like that for an arena or a stadium or something like that. So what we're talking about now is what is our quantity? So we've talked about the quantity of area, signed area. We've talked about volume as a quantity. And now we're going to talk about length of a curve or arc length. And so here would be this would be a good application of that. So a more general example, suppose I have this function here, this pink function, like this, and I'm interested in knowing what is this distance along the arc? How long is that arc length? And we're going to use the units on the axes as our scale, right? So whatever units we're measuring x and y in is going to be what we measure this in. So if we were to walk along that, how far would we walk in terms of this unit? That's what we're asking. Or how long is that pink curve? So what do you think? Is it 8? Is it 9? Is it 10? What do you think? What is it? 12.9. How do you know that? Oh, does it say it? I thought you were smart, see? So it's actually all the way, so it'd be the equivalent of this whole length from 0 all the way to there, to 12.9. Do you believe it? So it's like you take that thing and you stretch it out. And there it is, 12.9. So that's what we're after here. That's our motivation in arc length. How long is the curve? How long is the arc length? So let's take a look at this. So this is going to be a similar type approach that we've seen before. What? X is going to vary through delta x intervals. And watch what happens. Watch what we're going to keep track of in each delta x interval. We're going to start extending a segment. We're going to start extending a segment starting from the left side of the interval that's tangent to the curve at the left side of the interval. And we're going to measure the length of that segment, that straight segment in each interval. Okay, so I'm going to stop it in the next one. So here's this interval now. I'm going to pause it right there. Pause life. And so what are each of these things? So what symbols and what's the meaning of that quantity? That's number one. What symbols, what's the meaning of this quantity right here? That's number two. What's the meaning? What symbols do we use for this quantity right here? That's number three. And then what about this one right here? That's number four. Okay, first one. What's our symbol for that? What does it mean? Number one, so this length right here, which is also this length. What is that? Delta x. That's our fixed chosen interval width, right? Delta x is our fixed chosen interval width through which x is going to vary through all these delta x intervals, right? What is this then? So here I am in the current, this is called the current interval right here. This is the current interval because that's where x is. So x is here. What about starting from the start of that interval out to the current value of x? Good, dx. dx, and dx varies through the current interval, right? As x increases, dx varies starting from what value? But what the value of dx is what? Yeah. It's 0, right? It's the width. It's how far you've gone in the current interval. So dx doesn't start at the x value of the initial. It starts at 0. And then what's the maximum dx gets? Delta x, right? So right here at the start of the interval, when x is at the start of the interval, dx is 0. There's no variation through the interval yet. Now x grows from 0 to delta x. Sorry, dx. dx starts at 0, and as x varies, it grows up to delta x, and then it starts over at 0 again in the next interval. Does that make sense? Sorry, that's not well drawn. So dx is how much variation you have in the current interval, how much x has varied through the current interval. So it starts at 0, dx is 0, and then its maximum value is delta x, and it takes on every value in between 0 and delta x as x varies through the interval. Okay, so this is up here, so that's this little triangle up here, that's dx. So then what would this be? dy. Okay? And then this is going to be what we're going to use to build arc length. Okay? We're going to use that hypotenuse to build arc length, and that's ds. S stands for arc length, so this is ds. So S is arc length. So ds is how much like linear arc length we have in the current interval. Right? How are we going to get dy? dy equals mdx. dy equals mdx. Now, in all the examples we had before, we were given m, right? We had the rate. Now, so what is m here? So m is what? It's the, actually, now we're talking geometry, it's the actual slope, right? It's the slope of that line. And where do we get the slope of that line from? Well, it was the slope of the curve at the start of the interval. What gives us the slope of the curve? If this function is f, then what gives us the slope of the curve at any value of x? The derivative, right? The derivative would give us the slope of the curve. Derivative is rate of change, but in this case, this geometry sense, the rate of change is the slope. So the slope is the rate of change of x. So this is our function f. So it's the rate of change of f. But it's the one at the we get it from the one at the beginning of the interval, the left side. So particularly, so this dy is going to be the slope dx. It's going to be the rate from the left x value of the interval dx. Because we're pulling off that rate here, and then we're just letting that rate be constant for the whole interval. So this right here is the value of left x. It's the value of x at the beginning of the interval. That's where we want to get the rate from for that whole interval, so that we have a nice straight right triangle. So what are we interested in? If we want to get an arc length function, we need what? What do we need if we want to get an arc length accumulation function? This is a big theme of this course so far. The rate of change of arc length. The rate of change of arc length will be ds dx. So we need to get ds dx. If we can get ds dx, the rate of change of arc length, then we can write an arc length accumulation function, just like we've been doing all semester. Use the template, use the integral template, plug in the rate of change of arc length, and we got it. So where's that going to come from? Where's dx going to come from? What's the relationship of dx, dy, and ds? What relationship can we use there? Pythagorean theorem, right? We're going to use the Pythagorean theorem, and out of the Pythagorean theorem, we're going to get our rate of change of arc length, and then we can write arc length accumulation. So I'll just show that on the screen. So this will all be saved on the video. It's not hard at all. Pythagorean theorem says ds squared equals dx squared plus dy squared. Take the square root of both sides. Just watch and take the notes later. Then I'm going to plug in what we said with dy. dy was r f of left of x dx, right? m dx. Plug in our m dx for dy. And then we're going to factor out dx squared and then get that out of the square root. And there you have it. It's not hard. There's not much to this. Start with the Pythagorean theorem. Use our m dx for dy. And then there it is. So there's our rate of change function. It uses the rate of change of whatever curve. So f is the curve we're measuring its length. We're going to use the rate of change of that curve. But when the delta x intervals get really, really small, what does left x become? Just imagine the intervals being so small that delta x is like almost 0. Then left x is virtually what? No, not 0. X, right? So it's like the delta x gets so small that it's just like every interval is the x value, right? It's the current x value. So when delta x gets small, our rate of change function is, this is the rate of change of arc length, square root of 1 plus the rate of change at x. Not left of x, just x now, squared. So you're going to take the derivative of your function and plug it in here. Square it, add 1, square root, there's your rate of change, and then you can write your arc length function.